Okay, so in this video I'm just going to review a little bit of basic linear algebra stuff. The motivation behind that being that basically if you understand linear algebra, all of quantum mechanics is just linear algebra. So if you understand linear algebra, you understand quantum mechanics. Obviously, there's a lot of linear algebra and hence a lot of quantum mechanics, so we're not going to review all of linear algebra, but we're all going to review enough to study simple quantum mechanical systems, and then obviously we'll build into more complicated things later. So to start off, we start with, this is hopefully a review of just a basic two-dimensional vector space. And I'm just decomposing this vector v into these two basis vectors. So I'm writing v as a linear combination of these basis vectors, where my coefficients, c1 and c2, are just given by the dot product of v along the appropriate basis vector, which is like the projection of v on v1 or v on v2. And then normally when you work with vectors, you represent them using these column matrices. So I have this symbol here, this equal sign with a dot over it, and that's just going to mean represents. So I'm representing this vector v with this column matrix here. And so notice that the vector v contains more information than the column matrix here. Here I've got these coefficients, c1 and c2, and I tell you, what basis vectors I'm expanding this vector v in. Whereas with this column matrix, I only have the coefficients. So I'm not telling you explicitly what basis I'm expanding, this vector in. And that's fine if you're always working in the same basis. But if you change basis, obviously if I expanded this along different basis vectors, these coefficients are going to change, and so my column vector is going to change. So that'll just be important later on to distinguish between a representation of an object and the object itself. And obviously, I can represent these basis vectors using these basis column matrices. So I can build any column matrix out of a linear combination of these two column matrices. So that's cool. So the next thing I'm going to do is just redo all of this, but in a new notation. So I'm just going to take instead of using vector symbols over my labels, I'm going to put these labels inside what are called kets. So yeah, so let's just do that and see what happens. So again, I just have my vector v that I'm writing as a linear combination of my two basis vectors, and I can represent that by a column matrix still. The only new thing is that I have this new notation here. And so instead of the dot product, I have this weird, I've basically sandwiched two kets. I've turned one ket around and then smashed it into the back of this ket. And so this is called an inner product. It's just you still think of it as a dot product. It's not anything more complicated than a dot product. It's still a projection of v onto v1. It's just a new notational thing. But I do need to define this new object. So this backwards ket is going to be called a bra. And basically, basically for every ket, there is a bra. So if my ket is given by, this is kind of a general expression for a ket. If v is given by c1 b1 plus c2 b2, then my bra can be expanded in terms of basis bras, where my basis bras are just, the flipped around basis kets. And the coefficients are going to be the complex conjugate of the coefficient of the corresponding basis ket. So you can see kind of how it works out. And I'm going to represent these by row matrices. And I hadn't mentioned before, but in quantum mechanics, you deal with complex vector spaces. So all that means is that in general, these coefficients, C1 and C2, can be complex. That doesn't really add anything, difficult, any more difficulty, just as long as you're comfortable just multiplying and whatever, doing whatever with complex numbers, which I don't think is tremendously difficult. It's not any more complicated, really. And another consequence of it being a complex vector space is notice how, obviously, when we were dealing with real vector spaces and did dot products, v1.v commuted with v.b1. So it doesn't matter the order that you did the dot product. And we can kind of wonder, is that still true in a complex vector space? Is b1v the same as vb1? And we can work that out using these representations of our, kets and bras. So b1v is given by the, b1 is represented by this row matrix, and then v is represented by this column matrix. And I can just do this matrix math here, just 1 times c1 plus 0 times c2, that's c1. But if I compute v with b1, well, v is represented by this row vector, c1 star, c2 star, and then b1 is this column vector. And if I do this, I get c1 star. So it's so these are no longer equal to each other, but they're equal to the complex conjugate of each other. So again, that's not that big of a deal. They're almost equal to each other, but yeah, not quite. So that's all the vector stuff I want to do. Now I want to talk about operators. So an operator, what it does, and I'm going to use a notation now where, so before I was using this caret symbol, whatever it's called, I used for basis vectors. Now I'm going to repurpose it and use it for operators. So O is an operator, and all that means is that when you act an operator on a vector, you get some new vector. That is what an operator does. It just takes you from one vector to another vector. And so something that will probably be new, maybe, depends who you are, is that just like I can write my vectors as a linear combination of basis vectors, I can write my operators as a linear combination of basis operators. And my basis operators are going to be the so-called outer products. So inner product, you do this. Outer product, you do kind of the opposite. And so I've got this linear combination here, and just like I represented column matrices, but my vectors by column matrices, I can represent these operators by square matrices. So you can see this, so to do outer products, I basically have, so b1 is the column vector. I can represent it by this column vector, and then the bra b1 I can represent by this row vector. And so I have these kind of just outer product of these column and row matrices. And the way you do that is you form a matrix out of this just by doing the top, basically the top element times the left element is the top left element, the bottom element times the left element is the bottom left element, and so on. So you can see out of these outer products, I form these basis matrices that I can use to form any 2x2 matrix that will act on our column vectors.